Hi, welcome back. In this lecture, I would like to describe a simple application of finite difference technique. In this lecture, we're going to solve the Maxwell equation in the electrostatic limit. What is the electrostatic limit? The electrostatic limit is when the current and the change of currents are small enough not to generate a significant magnetic field and inductive electric field. In this case, we can use the Gauss law among the four equations. So we're going to use only the Gauss law, and then use the definition of electric field as minus the gradient of a potential function. So the right side of the slides show the process to get the so-called Poisson equation. We start from the Gauss law, the values of E equal to rho over epsilon. By applying the definition of epsilon as minus the gradient of potential phi, we can take the divergence of minus the gradient of phi, that is equal to the minus the Laplacian of phi. So we just use this identity of the numbers. The Poisson equation is Laplacian of phi equal to minus rho over epsilon. And in this lecture, we're going to learn how to solve these Poisson equations on a grid using the finite difference. The problem that we want to solve is the so-called Poisson equation in coaxial transmission line, and is the following. So here you see a section of our coaxial cable. We assign a potential in the inner part, so the blue part here, and the outer boundary. So we will fix a different potential between the inner boundary and the outer boundary. And then what we're going to do is to calculate the electrostatic potential in this region here, between the inner boundary and the outer boundary. Once we calculated the potential for each grid point of this area here, we're going to calculate the charge per unit length from the potential, and from that we are going to calculate the capacitance per unit length from the charge. So the end result will be the values for a capacitance of a coaxial transmission line. So the first step in our problem is to solve the Poisson equations on our domain. The Poisson equation in 2D is the following. This is the second derivative of 5 in space, that is the following expression. And since there is no charge, the right side here is equal to rho. So for the inner part, and we will fix the potential of the inner part equal to 1, and the potential on the outer boundary equal to 0. So there will be a difference in voltage of 1 volt. The first step we need to do is to discretize the Poisson equation and apply it on the internal points xi, y, j on the grid. So the equation is the following. We derived this equation from the previous lecture as just a simple algebraic equation. So each point of the grid will have an associated algebraic equation describing the Poisson equation on the grid. As the boundary condition, we're not going to use this equation here, but we're going to use two conditions. So one is a constant phi 0 on the outer conductor and phi equal to 1 on the inner conductor. Once we calculated the potential inside the coaxial cable, we're going to compute the charge, and from the charge we're going to compute the capacitance of the coaxial cable. To solve the linear system arising from the discretization of Poisson equation, we're going to use a technique called Jacobi and Gauss-Held iteration. The beauty of this method is that it doesn't require the system or linear equation to be formed and stored explicitly. However, we're going to ask you to think about for your assignment how you're going to formulate the problem in matrix form. So the Jacobi and the Gauss-Seidel methods are iterative methods. So they start with the initial guess for the solution for each point of our coaxial cable, and then we iterate all over this value. So for instance, at the beginning we can set all the value equal to 0, and then we start iterating, and then the values will change to something else. So it's called the iterative method because it updates the values until we reach a convergent solution that satisfies the finite difference approximation at all internal grid points. So how do we impose the boundary condition? Well, here is simple. We can just set it up Fi and j on the inner and outer boundaries by setting up prescribed values on the boundaries. The Jacobi iteration for the Poisson equation is the following. So in this expression, n is equal to the iteration. So we will have a series of iterations until the convergence. The initial guess will provide the iteration at time 0, at n is equal to 0, and then we can use this simple formula for calculating the new values of the function at a certain point. So the new value of the function at a certain point, ij, is basically calculated as the average of the potential of the 4 nearest neighbors. So I minus 1, j, I plus 1, j, j minus 1, and ij plus 1. So these are nothing else than the neighbors on the grid. So this is a very simple scheme. We can do something a little bit better that is called a Gauss-Haldy iteration. The reason for that is that the convergence of the Jacobi iteration is quite slow, so it will take many iterations to get the real correct results of our potential in the inner part of the domain. One modification of the Jacobi iteration we can do is the so-called Gauss-Seidel iteration, where the old values of our function f are immediately overwritten by the new ones as soon as they are computed. So we will have an iteration going through each grid point, and for each point we can use, instead of old point, the one that we have been just calculated. So in the case that f is updated in order of increasing I and j, the Gauss-Seidel scheme is very similar to the Jacobi. The only difference is that we are going to use the new values at iteration n plus 1 for calculating the iteration. Another approximation that we're going to do is to compute Poisson equation just on 1/4 of the domain, recognizing that there is a symmetry along this axis here and a symmetry along this axis here. So what we're going to do is to generate a grid such that the conducting boundaries fall on the grid points. And then we're going to exploit the symmetry and compute only the upper right quarter to reduce the number of unknowns. So in this case, I'm just using the lower left part of the domain. What we're going to do is to apply a symmetry condition on this boundary here and here around a line of symmetry with a constant. So how do we enforce the symmetry? Well, what we can do, we just enforce this equation on the boundaries where we have the symmetries. We just put that the function at the point I plus n is equal to the one I minus n with respect to an axis. Symmetry lines with the context j are going to be treated in the same way. So it will be the j plus n point will be equal to the j minus n with respect to the line. The other things we're going to do is to introduce the boundary condition by setting our f values equal to 0 on the outer conductor and equal to 1 on the inner conductor. And then we are going to iterate the Gauss-Seidel scheme over the internal points to serve the potential. Once we converge to the final solution of our potential, we can calculate the capacitance. But before the capacitance, we need to calculate the Q that is computed from the Gauss law, calculating this integral here. Once the charge is calculated here, we can calculate the capacitance per unit length as Q, that is the charge per unit, divided by the voltage. So we provide on the website a matter by code to simply calculate the capacitance values, providing a number of parameters, for instance, the size of our coaxial cable, the total number of points, and the tolerance that will tell us when to stop the iteration of our solver. If you use the code and then you plot the results using different and plotting different results at different iteration. So we start from initial guess that is equal everywhere is equal to 0, and we see that increasing the number of iteration, the potential is converging to basically a straight line. So this is the slide of this lecture. I'm going to ask you to perform this test and the practice by doing a convergence test, so increasing the number of grid points. And also we are going to ask you to try to formulate the Poisson problem and the coaxial cable as a linear solver problem using a matrix formulation. Talk to you soon.